All right, I'll actually get started now since I have some logistics stuff to go over. Um, so hey, my name is Jake, Jake Lee. I am the lecturer for the second half of this course. Dr. Uma Revapragada did a fantastic job of covering all the lectures on the first half of the quarter. From now on, from starting at deep learning, moving on to probabilistic models and such, I'm going to be doing all the lectures. Hopefully you see my name on Piazza and other places as well. So hopefully I'm not too unfamiliar, but we'll kind of get to know each other as the lectures go along, okay? All right, so just to start on some logistic stuff, so I'm going to have my own office hours as well. I just wanted to do a quick poll and ask if I did like an hour after each lecture on Tuesdays and Thursdays, are there courses scheduled after this course that conflict with that? You know, if I do it Tuesdays and Thursdays, no? Okay, so I figure we can do the lecture each day and then we can walk and talk kind of all over to Annenberg and then, yeah. Oh, okay. Gotcha, okay. So how about I'll do one of the office hours after one of the lectures and then sometime earlier. I know Uma did Friday morning. I might do that schedule-wise, we'll see. But I might do that instead. Okay, I'll aim to do that. So I'll do one, let's say, is Tuesday better or Thursday better? Let's do Tuesday after the lecture. I'll do 1 hour office hours, and then I'll find another morning slot to have another office hours. And both of those will be in the same Annenberg 343 room that Dr. Robert Picado was using. Okay, good. All right, in terms of course schedule, so let's see here. Homework 3 is due today. That was after the extension, so you've had a week and a half to work on that, so hopefully you can get that in. If not, remember you have a 48-hour global pool of late hours you can use between the different assignments. I do recommend you save it up for the later assignments, but if you need to use it, just use it. If there are other extenuating circumstances, such as medical issues, health issues, even like academic competitions that kind of took away the time that you might have spent working on the assignment, just email me. I'm pretty flexible with deadlines. So just don't hesitate to reach out if there are any circumstances by which you need a homework extension. The only concern is that if you receive too long of an extension, it'll set you back on the next assignment, right? But yeah, just email me. We'll work it out. Okay, so homework 4 has been released already in a timely fashion. We're getting better at that. You can see that on the GitHub and you can scroll through it. This is all about deep learning. You're going to be kind of answering some questions on deep learning principles, and then you're actually going to code up a neural network in PyTorch and playing around with architectures and such and trying to achieve a certain performance level on MNIST. Pretty standard toy dataset stuff. If it were up to me, I would make you code an entire neural network from scratch in NumPy, but I don't think we have time. So that's why we're resorting to this. It is a fun exercise if you want to do it on your own time, in my opinion. But things like PyTorch and TensorFlow now are mature enough that you don't have to do that. So that's why that's there. Yes?
Are all the sets going to be in PyTorch?
Yes, they'll be in PyTorch. I'll talk about that in the lecture a little bit. Yeah. Okay, so that's set 4, and then that'll be due next week. And then after that, we have our first project. So projects are different than homeworks in that there's no like answers. It's more like achieve this and write up a report, almost like a research report afterwards. Those can be done in teams, so that's a little bit unique. So a group of students can submit one assignment. I strongly recommend that you do it in teams, especially if you want to get more out of it and also practice collaborating with other students. So start finding those groups now. Yes? Yeah. No, it's not high school. I'm not going to assign you teams. Yeah. So try and find a good group to work with. If you can't, I think there's a Piazza feature where you can find teams. I'll turn that on, and we'll try and get something going there. But it'll be fun. We're trying to look for, I think they used so it's a Kaggle competition, so you're trying to achieve the best classification performance possible. We used a loans, like peer-to-peer loans data set previously, but I don't like finance data sets. So I'm trying to find like a JPL space-related data set, or at least something a little bit more interesting. So once we find that, we'll release that, and we'll talk about that. It'll be fun. There might be prizes. I have to clear it with admin, but yeah. I think there is. We'll specify the policy when that's released. Yeah. I think like 3 or 4, I'm guessing. But yeah, it's written down somewhere. I'll find it. Okay, let's see here. That's about it. And then on deep learning, so this lecture is on deep learning fundamentals. Next lecture on Thursday is going to be on convolutional neural networks, which is for computer vision and other things, but mostly for computer vision, and recurrent neural networks for time series / sequential data. For both, this is a textbook that I strongly recommend. In fact, this is the only textbook I ever bought in undergrad. Don't tell my alma mater that. But this is all free online. That's the best part about this, is that all the PDFs are available online. It goes through everything step by step. So if you really want to get into the weeds and understand how everything works and what's available, strongly recommend this textbook. You can also buy it as an actual physical book if you're into that. I just like postmarking things and things like that. Okay, all right. I think are there any course logistics questions? Oh, homework 1. Collab notebook, please submit a regrade request. That's like an easy 8 points that you're losing there. Yeah. Okay, all good? Cool. All right, let's get started with lecture. Okay, so actually I should introduce myself. So I'm Jake. I'm a data scientist at JPL. A lot of my specialty includes deep learning on kind of big data problems, so a lot of satellite data such. That means I also get to work in a lot of different fields, including atmospheric science, environmental science, onboard spacecraft science autonomy, which is a little bit more niche. I worked on like an Enceladus Europa mission like last year. That was super cool. So if you have questions on that aspect as well, come to office hours. More than happy to talk to you about my projects, and I'll try and throw in some experiences in here during the lectures as well. But here's a little lecture on deep learning. So these slides are by Joe Marino, who I think is Professor Isong Yue's PhD student. So these aren't my slides, so bear with me a little bit if I skip through them a little bit. But these are also available online for you to reference afterwards. Okay? All right, great. Okay, so a quick introduction. I'm going to go through a lot of stuff that you've already learned, but we're going to learn them in the framework of this assignment. So they're a little bit different representation of the same topics that you've learned already. And especially in deep learning, you're going to find that this continues. There are things that you can view from different perspectives and interpret in different ways, even though they're the same thing. So just kind of keep that in mind as we go forward here. Okay, so in our classic machine learning problem formulation, we have our data, and we have the labels, and we seek to predict the labels from the data, right? And depending on the task, if y is continuous, then we're trying to do something called regression, right? Where we try to predict a specific value from your input x, because you're trying to predict that line, essentially. Or, as we've also done, if y is binary or categorical, then you're trying to do classification. You're trying to bin those input data into specific categories. The example shown here is binary, right? But it could be multi-class, right? There could be multiple classes that you're trying to predict between. So this is, we know this already. So going through a classification example, just to, again, set the stage for what we're going to be talking about. This is a problem that you should be very, very familiar with, having done this in homework 2 and homework 3. Where we have some data set in 2 dimensions, x1 and x2, and we're trying to find a hyperplane, in this case a line, that separates those 2 populations because they're linearly separable. Right, so what we've done so far, we're trying to use logistic regression to find a linear decision boundary. And we do this by defining some loss function, right? In this case, the binary cross entropy, also log loss, they're the same thing. I don't know why they do that. It's kind of confusing, but they're the same thing. So we try to learn some weights, W, and some bias, B, because that helps us, frees us from 0, 0. And we minimize the binary cross entropy to find the optimal weights and the bias, right? And we do this by doing gradient descent. So we calculate the gradient W with respect to the loss function L, and then we subtract that from the weight, and then we do the same exact thing for the bias. The only reason they're notated differently here is because W is a vector, right? So we use the gradient symbol. whereas for the bias, it's a scalar, so we just do partial derivative of the loss with respect to b. And going forward, I know this is a little bit confusing sometimes because sometimes biases are formulated as weights with respect to a one feature. Same thing, just kind of practice sticking back and forth there. But we're trying to refer to the same thing. Okay, so everyone's comfortable with this, right? I hope so. Great. Okay, so there are some cases where we have to do classification, but the data set is not linearly separable, right? So in this case, we have this data set, and we've already drawn some separating line here, but it's clearly not linear. So we need to find a non-linear decision boundary. So one option to do this is to not use linear terms. So I don't know how much of this we covered in previous lectures, but just to do this again, right? If we expand x and derive additional features like x squared, x times, well, okay. I'm trying to use x and y, but it's x sub 1 and x sub 2. So if we derive additional features such as x sub 1 and x sub 2 squared, or x sub 1 times x sub 2, we can actually convert this non-linear, we can convert this domain in which a linear separator doesn't exist into a higher dimensional space where a linear separator does exist, right? So we're transforming the input space into a linearly separable space, if that makes sense. Before I move on there, this is actually fairly common. This is, this used to be the rage. Also, like feature engineering. If you came to Dr. Lucas Mandrick's talk, he talked a lot about feature engineering, right? And a lot of times, this is our kind of initial go-to, especially if you have enough a priori information to design those features, right? That might be what you want to try initially, because a linear classifier is always going to be the easiest to do. Option 2 is instead to use multiple linear decision boundaries to compose a nonlinear boundary. So if you can't do it with a single line, draw multiple lines, and that way cut up the space into some subregion by which you can classify this non-linearly separable example. So in this case, you can actually consider that we're splitting up the space. So don't take both of the decision boundaries together. Take it one at a time, right? So if we take the first one, so let's say, I'm going to use chalk here, right? If we do that one first, right, we have a homogeneous population here, right? And then on this subspace, now this part is linearly separable. So now all we have to do is draw that second line, right? You might see some parallels to the tree-based methods that were covered in the previous couple lectures, but it's kind of a similar type of an idea, right? Okay. But the point being is that in both cases, we're transforming the data into a representation that's linearly separable, right? Because we know really, really well how to find a linear decision boundary if the data is linearly separable. So just change the data so that it becomes linearly separable. That's the idea. Okay, so just to kind of make this a little bit more concrete and just to show an example that's been very, very extensively studied, we're going to go over Boolean operations. So if you're kind of in the electrical field or computer engineering field, you'd be very familiar with this. We have a, I don't know if it says y here. Oh, okay, sure. All right, so we have some space, x sub 1 and x sub 2. X sub 1 is either 0 or 1, and x sub 2 is either 0 or 1, Boolean, true or false, right? And then we have the labels y, where the two different colors are the two different classification bins, right? So 0 or 1. So we're trying to draw this linearly separable hyperplane. So if we have and or, this is fairly simple, right? You draw that diagonal line, bing, bang, boom, you have classification. But XOR, which is exclusive OR, which is either x1 is true or x2 is true, but not both, right? As, again, visualized in that graph. That is not linearly separable with a single hyperplane. You would know this because this was on, I think, homework 1 or homework 2, where you had to say what are the minimum number of points that are not divisible, linearly separable, right? And so in this case, it's 4. It's because of this XOR example. So XOR is not linearly separable, but as I mentioned in the previous slide, if you use multiple dividers, then in fact you can do this classification. So this, I don't know how much these slides are going to talk about it, but this problem was actually when the perceptron was initially proposed back in like the 70s or 80s. The discovery that the perceptron can't learn XOR was one of the kind of factors that contributed to the AI winter, which is like a period of like a decade where not much AI research funding or not much AI research efforts were done, because it was like, well, if you can't even solve XOR with this perceptron method that you came up with, then what's the point? I'm massively simplifying, but I'm kind of trying to say it looks simple here, but at the time, or like fundamentally, this was a very important problem, classifying XOR. So you can actually build XOR with the and or operators. And again, if you're in computer engineering or electrical engineering, you're very familiar with this already. And this is how you do that. So you have an OR gate and a NAND gate. Again, trying to use electrical terms here. We have an OR gate and a NAND gate, and then if you take the AND of those two outputs, then you get to classify XOR, right? So this was kind of what brought us out of that AI winter, is we can, in fact, chain these Boolean operators to classify XOR. Can we model our perceptron classifier similarly to achieve the similar thing, right? Yeah, we might ask you to do this on the final. I'm just kidding. We don't know. I don't know what's on the homework, but this kind of, we might ask you, we have this kind of non-linearly separable problem. How would you, by hand, build some chained perceptrons so that you can achieve a certain classification? I think there's a version of this on the homework as well, so you'll get some practice and some intuition on that. Okay, so just to recap this point that I've kind of delved into probably too long, in order to fit more complex data that's non-linearly separable, which is most data in the world, by the way, we need more expressive non-linear functions. We can do that by we can either do that by doing feature engineering, so transforming your input space into something that is linearly separable, or by composing stages of processing. So kind of trying to link this back into deep learning, the depth here would be the number of stages of processing, so the number of lines that you draw, the number of times you cut this input space. And deep learning, by definition, would be attempting to learn those functions that have those multiple stages of processing. Any questions so far? Pretty straightforward. Great. Okay, so why not just use nonlinear terms? Does anyone want to give it a shot? Yeah. High variance, okay, sure. So there could be more noise. Yeah. Any other? Yeah.
You don't necessarily know which.
Okay, sure, right. There's a lot of different options that you could do, right? It doesn't have to be quadratic. Do you have to go up to like power of 5 or come up with more complex stuff? Okay, so you certainly can, but like you said, there are some difficulties to doing this that are obvious up front. And the fact is that by using enough stages of linear boundaries, by composing enough linear boundaries, you can actually already approximate any nonlinear function. So kind of the empirical answer to this is because we have an easier way of doing it, so we kind of prefer not to do it this way. Okay, let's actually get into deep neural networks. Any questions up to the formulation so far? So this stuff is still very important, right? This kind of sets up the stage for defining the problems that we're trying to solve with deep neural networks, other than the fact that it's quote unquote better than everything else. Okay, great. So let's define some terms. So this is an artificial neuron. And throughout this, you'll kind of see a lot of neuroscience adjacent terminology. This is because initial designs were kind of inspired by neuroscience. In fact, NeurIPS, which is like a big machine learning conference up there with ICLR, ICML, AAAI, right? Used to be a neuroscience conference and then it kind of got taken over by machine learning, or at least that's the story. So those fields are kind of adjacent, but please don't go around telling neuroscientists that we're trying to imitate the brain with deep neural networks, right? It stops at inspiration. The actual mechanisms and et cetera are quite different. So that's like a pet peeve of neuroscience friends. It's like, oh, we're trying to imitate the brain with neural networks. Like, don't say that. Anyways, okay, so we have artificial neurons. We have these input features. These input features, multiply them by weights, and then we add them, very similar to a perceptron, right? We kind of covered this already. The one major point that's different here is the nonlinearity. We also call this the activation function, again, from neuroscience. But this nonlinearity is crucial to deep neural networks, and we'll kind of explain that later. But we call this entire node a single neuron. So when we take these neurons and we kind of copy them into a bunch of them on the same inputs, we call that a layer, right? So when we say multiple layers in a deep neural network, this is a single layer. They all take the same inputs, but they all assign all their different weights into their sums, and then they generate an output. And then using those layers, we can stack them horizontally, and that's how you get a network. So that's each layer is a depth. So you have that input layer on the very left, and then you do that once, that's a single hidden layer, right? And then we do that second time, that's a second hidden layer, and then whatever the output is, that's the output in the end. Why is this? Oh, there we go. Okay, so just to put it in math, because that's how we've been talking about it so far. Again, artificial neuron, the top line should be very familiar. It's like a perceptron, right? Again, note that this time we're talking about bias as W0, W sub 0. That's the same thing as the bias. Depending on different neural network resources you read, they'll refer to it as B instead of W sub 0. Just keep that in mind. Again, so we add them together. And then, again, critically, like I said, for neural networks, we add this nonlinearity function, sigma, to that sum, and then we get our output feature. Okay, so the thing I like about this slide deck is that it has these matrix visualizations, and these are actually really important because as you go through these, it gets really complicated because you start chaining these, and then you start having different dimensions, and then you write your code, and then PyTorch says dimensionalities don't match, and then you get frustrated, right? So we're trying to build this intuition of what the neural network is doing, and we're trying to keep track of the matrix dimensions as we're going through this process, okay? So again, just to draw this out, we have our weights horizontally, W transform, and then we have our input features, we multiply them to get the sum, and then we apply the nonlinearity, and we get our output feature. That's all that's saying. Okay, so let's look at a layer. So the great thing about neural networks, and part of the reason that they were so popular fairly recently, especially with new compute technologies and such, is that it's very easily parallelizable because computers are very good at doing linear algebra. There's a lot of other computing problems that require linear algebra, so we've spent a lot of resources developing processors that are very specialized for linear algebra, like GPUs and other TPUs and FPGAs and other things that we've come up with to just do linear algebra, right? Even CPUs have dedicated instructions, low-level instructions just for linear algebra. So neural networks are great because linear algebra, everything is parallelizable. So for a layer, we can actually do this entire thing in one go. So instead of one sum per weight vector, right, we have multiple weight vectors that forms a full two-dimensional matrix instead of a one-dimensional vector, right? And then we can just multiply that by the input, and we can calculate the output of an entire layer in one go instead of having to do it node by node. That's by design. That's very that facilitates the compute quite a bit. And then expressed visually, just so again we're trying to build this intuition. You have a single input, and then we have multiple weights, and again we can do this matrix multiplication in one go. And then the nonlinearity. I'm not going to let go of that. If you forget to add an activation function in PyTorch, it will not work. And again, we'll explain later. Okay, so now ending up at the network, again, we're building up this neural network as we go forward. It is a sequence of parallelized weighted sums and nonlinearities. So unfortunately, we can't parallelize this. You do have to go layer by layer, which means there's a lot of compute overhead for very, very deep networks. But again, we're just going to chain the equations forward. You do the first layer, you get your sum. You do your activation function, you get the output. You feed that straight into the second layer, multiply it by the weight, get the sum, activation, etc. Shown via a diagram here. The way it's shown, it's chained, right? So start at the inside. So, oh boy. That's the original input. That's layer 1. That's activation 1. And then this is layer 2, activation 2, and so on. So inside out, right? I'm going to be pretty mad if I go forward in the slides and, yep, okay, never mind. Okay, I don't have to do that as labeled. Okay, does that make sense to everyone? Good? Okay, this is really important. Otherwise, you'll get confused when we get to CNNs because it gets kind of more complicated. Okay, great. So quick recap, we have now a method for building expressive nonlinear functions by combining and chaining and layering these perceptrons with activation functions, these neurons. And it's actually shown that deep networks are universal function approximators. So what does that mean? So that means that given enough depth and given enough width, so a network of infinite depth and infinite width, this is how mathematicians think, right? You can actually approximate any function within some epsilon, right? So if you have enough model capacity, it'll approximate any given function. That does not guarantee that we'll be able to learn that function, right? And that does not guarantee that we have the computational resources to do that approximation, right? To actually support a network of that size. But at least the concept is, the theory is if you build a large enough network, you will be able to approximate any function. And this is like mathematically proven, and then people have tried to prove different bounds on it, et cetera. There's a whole field of theoretical neural networks, right? That gets a lot more into mathematics, computational learning theory, et cetera. Great. Okay, so we're going to go into a very interesting reinterpretation. And this is actually new to me as well. I only saw this as I was prepping these slides. And I think this is a really good way of thinking about it, because this kind of goes back to where we were talking about producing new features to turn our domain into something that's linearly separable. So another way to interpret what neural networks are doing is like this. So the dot product, if you recall your linear algebra, the dot product is the distance between a point and a plane, right? So given some input, given some vector, it defines the distance between a point and a plane. Each artificial neuron then defines some hyperplane, right? So it's some separating hyperplane. Good. Now, calculating the weighted sum corresponds to finding the shortest distance between the input point and the weight. That's exactly what I said. Between the input point and the weight hyperplane, right? The orthogonal line on the separating hyperplane to whatever point that you were given. Now, the nonlinearity, and I keep harping on this because this is really important. The nonlinearity that comes after the summation transforms this distance, creating a field that changes nonlinearly with distance, monotonically, right? So I like the visuals in this slideshow. Again, so we have some separating hyperplane. We have that, we calculated that distance, but now we can actually transform that distance with the activation function itself. So again, we have the inputs. We calculate the distance of that point with respect to the weight vectors, and then we transform that, literally that distance metric space with the activation function. So this means that a weight vector becomes a filter when the hyperplane faces a cluster of points. And what we mean by that is that each unit selects for the abstract feature shared by the cluster of points. So if there's a group of points in this n-dimensional space, this hyperplane is facing towards it. So it selects, it filters for that group of points. And then every time it does this, it does that, and then the activation now kind of pushes that cluster further into its own cluster, right? Because it's stretching out the metric space. Okay, so visually, we'll try to clear this up because it's hard to think in n-dimensional space. We have this input space of purple and orange points, again, of different classes. And then the neural network on the first layer has these dividing hyperplanes, in this case in three-dimensional space, okay? That produces a new set of points that are now transformed so that it's a little bit more separable. And then the second layer, again, applies these set of three-dimensional hyperplanes, and that further pushes those points so that it's more linearly separable. And then finally, at the end, we have one output node, and this is how neural networks are built. We have a single hyperplane that's able to divide these points in this n-dimensional space. Okay, and by the way, we only do this in 3 dimensions and like 3 nodes per layer because our brains can't handle anything more than 3. But there's nothing here that says it has to be 3, right? It could be, even if your input points are in 3 dimensions, you could have 8 nodes, and then that projects those 3 points into 8-dimensional space, right? And then you can have 12 nodes after that, which then project those 8 points into a 12-dimensional space. But in that 12-dimensional space, those points will be linearly separable, and then that output node will finally be able to do that classification. Okay? So yeah, that's kind of enumerated here. Cut up the space, evaluate the distance, transform those distances according to the activation function, and then so on and so forth until the data set becomes linearly separable in whatever dimensional space it ends up in. Okay. Does that kind of intuitively make sense-ish? It's interesting. I do like this interpretation. Okay, great. So big picture, again, neural networks are functional approximators. The deep nature of it enables a broader set of functions than anything we've learned so far. They're very good at approximating general functions. It says on here, particularly conditional probability distributions. Sure. Okay. All right. Does anyone have any questions about the general architecture and how we build up a neural network? We haven't gotten to the learning part yet. We've only gotten to the actual mechanism by which a neural network functions. No? Okay, cool. By the way, how many students here have already done neural networks before, or at least tried building a deep learning network before, like on PyTorch or TensorFlow or on that? Okay, good. All right, good amount of familiarity. Okay, great. All right, so now we're going to talk about how we train these networks, so how we learn. So this is referred to as backpropagation. You'll see why. All right, so we still have to learn. That's all this slide is saying. So neural networks are approximators, but we still have to learn. And by the way, this hypothesis space, because neural networks are so wide and deep, this hypothesis space is massive, right? So unlike previous SVM or perceptrons that we've covered so far, where the weights are just the dimension of the input dimensions, because neural networks, now we have layers of neurons and layers in a certain depth, this hypothesis space is absolutely massive. So learning is always a challenge. So it's not infinite because the architecture itself is finite. So there's only a certain number of parameters inside the model, right? But it's still yeah, right. So a given certain architecture, then it's limited, yeah. But if it's an infinite depth, infinite width, yeah, then it's infinite, yeah. Okay, so we do this similarly to everything we did before, okay? So same thing with perceptrons. We just need the derivative of the loss with respect to the weight, or the partial derivative of the weight with respect to the loss function, right? Again, you've implemented this before, so you're familiar with it. With multiple weights, when it's a vector, we just refer to it as a gradient instead of the derivative, but same thing. All right, so the problem here is that a neural network defines a function of composed operations, right? So we're kind of nesting operations here. And the final loss is a function of the network output, right? So we have input, layer, output, and then the loss function against some label, right? So that means that we have to use the chain rule to calculate our gradients. This is an example of a chain. I will assume everyone here is familiar with calculus, but I will leave this up here just for a minute to refresh your memories. It's also been a while since I've taken calculus, right? But basically the idea is when you have nested functions like this, you can do U substitution and other tricks, right, to get the partial derivative of a single variable out of this composed function, right? The important part here is that box, is that chain rule, where the partial derivative of, what is that? Yeah, the partial derivative of w sub 1 with respect to y can be decomposed into this combination of partial derivative of y with respect to v, and then u respect to v, and then w sub 1 with respect to u, right? So you can kind of chain these partial derivatives together to get the final partial derivative. So the reason this is relevant to learning for a neural network is that we have the exact same thing. So we recall that the first layer, we have the weights times the input, sum, activation function, weight times the input, activation function. You chain that all the way through, and then that goes into the loss function. Yeah, okay. And then what we can do is we can walk our way back, okay? So here, this is kind of a dependency graph of a neural network. You'll see this quite often. It's a very useful tool, especially as we get to more complicated architectures. But all this is defining is the information flow as it goes through the neural network, okay? So we have, again, let's just pretend this is the entire network. We have our input x. We have the weights of the first layer. We sum them, and then we do the activation is missing here, but assume that the activation is on this node, right? And then again, that generates some amount of features that then go into another weight, et cetera. And then finally, you compare that weight, that output with the target, the label, and then you have the loss function here. So if we kind of forget about the chain rule for a second, and then we imagine that we're trying to find out how to update just this first W, right? If it's a single layer neural network, now it just becomes a perceptron, right? So this is fairly simple, right? The derivative goes back. It kind of flows, it propagates back from the root node of the loss, okay? And then back to the thing that you're trying to update. So in order to calculate the partial derivative of w sub whatever layer you're trying to do with respect to the loss function, this means that you can actually calculate the loss function, the partial derivative of x with respect to the loss function, and then of the sum with respect to x. I guess the activation function is in between there, and then the partial derivative of w with respect to that sum, right? So if you just calculate those individual gradients, you can actually end up at the full update for the weight layer that you're trying to update, okay? Again, a quick note about the convention. Because it's a vector, we use the inverted triangle. And oh, I like this. Okay, so we have, again, the derivative of the loss, of just the loss. So if we just isolate the leftmost term there, that's just the derivative of the loss function, okay? And then we have the derivative of just the nonlinearity of the activation function itself, and we'll talk more about that. And then after that, we have the derivative of just the perceptron of the wx plus b, or w sub 0, if you're doing it that way. And by multiplying all of those, you can end up at the global update for the weight of that layer. And as you can probably tell, we can do this for all the layers. So for a layer that's one layer back, for a weight that's for a node that's one layer back, we just keep chaining. So we have the, let's see how far this goes. Yeah, there we go. So again, we have the loss function gradient, and then the activation function gradient, and then that first perceptron layer's gradient, and then we have the activation functions gradient of the layer before that, and then we have the gradient of the second to last layer's weight vector. Okay, does that make sense? Okay, good. So just follow the graph. Just build the graph forward, and then just propagate the graph back to where you started from. And because of the chain rule, this is really convenient. We can just calculate the individual gradients at each step of the way and end up at the update that we're looking for. The other convenient thing about this is that we end up reusing a lot of the gradients. So if we want to calculate the update for the last layer, and then we want to update the gradient, we want to update the weights of the second to last layer, we use the same, you can see it on the red arrows, those set of red arrows we're using twice, right? So that means we can save a lot on compute. We don't have to recalculate a lot of the gradients. So that means that we always start from the last layer and then go forward, right? Because that means any of the gradients that we calculated, we can cache, right? And we can reuse without needing to recalculate it for every single input, okay? So again, neural networks are great because we can take these little tricks, and architecturally, it's very easy to parallelize, as I mentioned before. And then even for the weight updates, right, there's a strategy by which we can cache previous calculations and use them for updates of other layers as well. Okay, so let's actually formalize this algorithm in kind of like a pseudocode way. So first, you calculate the derivative of the loss. So the loss has to be differentiable. We'll put a little asterisk on that, right? The loss function has to be differentiable. And then we store the partial derivative of the activation function with respect to the loss, which is the same thing as, sorry, okay, I'm one ahead. So this is the derivative of the loss function, and then the activation function afterwards as well, because that's going to be reused by everything, okay? So a partial derivative of the loss with respect to s here is the same thing as partial derivative of the loss with respect to x, which is just the loss function, and then the partial derivative of s with respect to x, which is the activation function. So those two arrows, we store that. We're going to use that over and over again. And then for each layer, to update the weight, we calculate the partial derivative of L, partial derivative of S with respect to L to the loss function, and then we just keep chaining back. So we use it, we store it, we go a layer back, we use everything we know up till now, we use it, we keep going back. It's just on an iterative way back towards the first layer. And then finally, now we know the weight, now we know the gradient updates for each layer, and then we can update our weights. No need to update the input, because that doesn't make any sense. Okay? Any questions on the backpropagation algorithm? Is that because I explained things so clearly, or because I explained things so confusingly? Everyone got it? Thumbs up? Okay, all right, I'm just making sure. Great. So, I don't know. I think when you first learn it, it's like, it looks kind of confusing because there's a lot of partial derivatives and like chain rule and things like that. But if you really kind of stare at it, and especially if you look at this graph here, it is kind of simple, right? It's fairly straightforward. You propagate forward to calculate your output, calculate the loss, and then even for calculating the weight updates, the chain rule makes things very easy, and you just follow that same graph backwards with your gradients. Yeah?
I know for like auto diff stuff,
Mm-hmm.
it has to store what should be being stored on the forward pass?
Yeah, that's a great question. So we'll talk about this a little bit later too, but there's systems like AutoGrad. The benefit is that you don't have to manually write out the derivative by hand. If you did do the derivative by hand, you wouldn't have to store anything. But what AutoGrad is storing is the compute graph, right? It's storing every addition and multiplication and every unit of differentiable function that you're doing, so that later on it can calculate the gradients going backwards. Does that make sense? So it's kind of on a operator level. So it's automatically calculating the gradient of some specified custom layer of some specified function that you're doing. It's not necessarily automating the back propagation, if you will. Does that make sense? Yeah. It's with the gradient function itself, like the differentiate. Like the first derivative function itself that it's automating. Yeah. Any other questions? All right. So, quick recap. We just use gradient descent to update the weights of our neural network. We do that with backpropagation. They call this credit assignment. Sure, we just use the chain rule to update each layer's weights. And like you mentioned, most deep learning software libraries automatically calculate these gradients because they make things convenient for us, called autodiff. I remember when back in like cafe days, like the really old deep learning frameworks, you had to define your own gradients and you have to do that propagation manually, right? So it's nice that these systems now exist. Yeah, so as long as you're doing any differentiable operation, and even if you define your own custom layer, you don't have to define the gradient of that layer. The system will just do it for you because it knows what operations you did in what order. Okay, all right, so that's kind of the theory part. I spent like a solid 50 minutes on that. Any additional questions about how and why neural networks work? Okay. All right, let's talk about implementation. So like I mentioned before, neural networks can be parallelized. The nature by which they can be parallelized, what we talked about was how, oh, shouldn't touch my mic. What we talked about was how we can parallelize each layer, right? So we don't have to do every node individually. We can just collapse them into a single matrix, and then we can do all of our calculations as matrix multiplication. So quick reminder, that's how that kind of works, and we call that unit parallelization. This is available by default. Most frameworks do this by default. The other thing we can do is we can do data parallelization. So instead of sending through one data point, we can actually send through n data points, 2, 4. These usually work in binary for some reason. So you'll see batch sizes of like 16 data points being put through at the same time. Again, we just stack it up like into a matrix, and then we send it through. Everything works just fine. So by using these parallel computing architectures, this makes neural network operations very, very efficient. And you can absolutely do these at the same time, right? So if you stack your units and then you stack your inputs, now this just becomes the multiplication of two-dimensional matrices, okay? So part of the revolution over the past decade or two in neural networks becoming so popular is that we have these CPUs that are becoming faster, right? Like exponentially faster and exponentially more efficient. We also have things called GPUs. I'm sure they've been in the news lately, NVIDIA, whatever. But GPUs are specifically cards that are meant for just linear algebra, right? Because computer graphics, if you're in that field, you will know, for ray tracing or rasterization or things like that, those are all just matrix operations, right? And GPUs actually have something called CUDA core. Well, NVIDIA GPUs have things called CUDA cores. Other AMD brand GPUs have something similar, where these are like 8,000 parallelizable cores, right? That are all specialized to do linear algebra operations, right? So that makes this process very, very efficient. Yeah. Yeah, sure. Right. Yeah, that's a great question. So the question was, how do you do the gradient update if you're sending in 16 data points at once? Um, you can like average it at the end. That's a strategy. Yeah, because in the end, you're still providing updates per kind of feed through, right? So as long as you're going down that slope, it does that. There's also something called, so that combined with batch normalization actually provides some amount of regularization for the model. I'll talk about that in a future slide, but yeah, I think we just average it. Yeah. That also means a batch size that is too long might actually regularize your model too much, especially if you have like some really imbalanced data set. So for example, let's say you're trying to train on a data set where there's 2 positive class examples and 1,000 negative class examples, right? If your batch size is too large, then they're going to get drowned out, right? If that makes sense. So you have to be kind of careful with having too many data points in a single. And that's for training. For inference, you can shove as much as will fit into the VRAM as possible, basically. But for training, yeah, you have to be careful with the batch size a little bit. Good question. All right, so real quick, going into the NumPy implement. You're not going to have to do this on the homework. We're going to use PyTorch. But let's just go through it just for fun. So, and if you want to do this on your own time, strongly recommend. Very satisfying when it works. Very frustrating when it doesn't. But if you want to try it, I strongly recommend it. So again, we just have a neural network layer. Let's do, right, so we have W, capital W, because it's a matrix and not a single vector, right? Multiply times X. And then we have np.maximum, that's our activation function. That's our nonlinearity, right? Here it's ReLU. We'll talk about that. Okay, and then what is this? Oh, you initialize your weights, right? And then when you call it, it returns the activation. And then it chickens out before it has to do the gradient update. Anyways, so again, the point being that most deep learning software libraries will automatically do this for you, so why bother? This is also because as you get to more and more complex neural networks with more complex structures, skip connections, things like that, gradients do get quite complex. So it's a good thing that we have these different packages to help us with calculating this backpropagation, where you just define the feed forward, just the forward-facing layers, and it takes care of the backpropagation for you, because that's the hard part. You might have probably heard of TensorFlow, PyTorch, probably less MXNet. Keras has become TensorFlow because it's an API, something like that. Cafe2, I don't think anyone uses. We're going to use PyTorch in this course, and I would recommend PyTorch going forward. Also worth noting, PyTorch is developed by Meta. TensorFlow is developed by Google, because that's how things are nowadays in computer science. But PyTorch is far more popular for research applications. There's like a nice website where every year of like NeurIPS and ICML and iClear, they take every open repository and they count which papers used which package. And it seems that PyTorch is more popular. TensorFlow is more popular for actual deployment. So MLOps, or like if you're Facebook and you need to run, well, not Facebook, but if you're Google and need to run, millions of models at the same time on millions of people, then you might go into something TensorFlow. Easier for deployment. It's a little bit more abstracted because of the Keras framework. But we're going to use PyTorch because it gives you transparency into what the actual model is doing, in my opinion. Yeah. Yeah. Again, I'd say I don't think learning one over the other is going to hurt you in the application process, because it's pretty easy to pick the other up once you kind of learn it. It's kind of like C and Java, right? Like the syntax and the structure is kind of similar in that, so you can pick it up. But I think PyTorch will leave you to be more flexible, just because, in my opinion, this is totally my opinion, not representing anyone here. If you learn TensorFlow, it's so abstracted. Like you call like model.train and then it like goes, right? Whereas in PyTorch, you actually have to do like, okay, feed in the input, get the output, calculate the loss, right? And then backpropagate this loss. So it's a little bit more granular. So I think the easier direction is from PyTorch into other frameworks, but that's, again, wholly my own opinion, and learn whatever you want. But for this course, you'll at least learn PyTorch to some capacity. Yeah. Yeah. I think companies, even if they have their own standard, they'll just onboard you on that anyways. So it's not going to hurt to learn one package over the other, specifically for recruitment, in my opinion. Any other questions? Is that a question? Yeah. Yeah. How regularization is applied. Yeah, I think it's in a future slide. Let me go forward a little bit, and then I'll get back to you if it's not mentioned. But I'm pretty sure it's mentioned. Okay. Is that okay? All right. Anyone else? All right. Cool. Tips and tricks. This is a weirdly innocuous section title for some important content, in my opinion. All right. So nonlinearities. Nonlinear is not tips and tricks. It's like critical information. Okay. So the activation functions, it's critical that these are nonlinear, because if you don't have them, it just becomes a single linear function, right? So because of the associative property of matrix multiplication, if you don't have these nonlinear functions in the middle, it just collapses into a single linear model, and now you just have a linear model. Congratulations, you just wasted a lot of compute, right? So please remember when you build your networks to include these activation functions or nonlinearities. Different nonlinearities result in different functions. Well, yes, optimization services. This is a very interesting topic, and a topic in which a lot of research has been dedicated. So let's go back. So initially, kind of the old school activation functions used previously was logistic sigmoid on the left and tanh to the right of that in blue. So this is kind of the initial nonlinearities were used. But the problem with these is that as the input goes to infinity and negative infinity, the derivative goes to 0, right? So what you have is the problem that you get is called vanishing gradients, where at any point in your model, if like the distribution of values kind of escapes that, it reaches that saturation point, like there's no way to update that node anymore. It dies. That node dies. So that's not good. So I think nowadays sigmoid is more reserved for just the output node. So let's say you have a bunch of layers, and at the end you need to get the output, right? And that output, you know for a fact, is from 0 to 1 because it's a classification task or whatever task that you're doing. You slap a sigmoid at the very end to kind of squish your values down to the range that you're expecting. That's more what it's used for. But there's other applications where they found that sigmoid and tanh is more useful. So kind of on a case-by-case basis, people just kind of try it. The most popular activation function by far is called ReLU, which is on the bottom left here, and we call this non-saturating because at any positive point of this domain of the x, the gradient is always 1, right? It never saturates, although you kind of get the similar problem in the other direction, where if the x is less than 0, then again the gradient is 0 and that node dies, right? So that's the reason all these other functions have come up, which is like leaky ReLU, right? So where the gradient is 1 in the positive direction, but like it's probably like 0.1 or like 0.00 something in the negative direction, so that node doesn't completely die, right? Or soft plus, which is a smoother angle instead of a sharp angle around 0. And then ELU, which is kind of exponential instead of linear. There's also something called swoosh, which I don't know what the exact formulation is, but they try to make catchy names for the activation function so that it gets more popular and other people use it, which is why they named it swoosh. I'm serious. Look it up on archive. Like it's called swoosh. By far, your best bet is just to use ReLU, see if it works. And then if you're really, really, really optimizing your network, for your specific task, then try some other activation functions for fun. But generally, ReLU will get you 95% of the way there, in my experience. And then also, we say that it dies at the negative x, right? That the gradient can update. But remember, because this is layers, right? Your input changes when your previous layer updates, right? So it's not like the node dies permanently, right? So it's possible that some earlier changes in the model will bring those input values into a range where you get a positive gradient again, and then the node starts learning again. Okay. Yes.
How come there's no activation function that's like that? Like if we have the property we want on the right side with ReLU, why don't we do the same thing to the left side? Why is it that choose to make it 0?
What do you mean? So just like
instead of making it like I don't know, like an absolute value or like just a line. I don't know, like why choose to make it like zeroed out?
Because it needs to be nonlinear, right? So it would just be a line, right? If we did what you said, it would just be.
Yeah. But like, I just mean, why do we prefer to have it be something like 0 instead of, I don't know, like just like randomly like.
Well, so it does need to be monotonically decreasing.
Okay.
So it does need to keep going down. It can't go back up because that's weird, right? Like you can't give positive feedback on a negative, right? But that's what all these other methods are trying to do is, provide some nonlinear activation. So add some nonlinearity to the model, but add their own little flavors to what the gradient should be when the value is not positive, right? Does that make sense?
Yeah.
Kind of. Okay. I will admit some of it is more art than science. In terms of why ReLU works, right? Like I don't think there's a paper that proves why ReLU is like the best activation function. But at least the concept is, and we covered this with, if you recall, for the perceptron, right? We mentioned, I think there's a Piazza question too, where they asked like, can you use any sigmoid like loss function for trading like perceptron, right? And then we said, well, yeah, as long as it's reflective over 0, 0, and it's monotonic and it has that kind of a nature, you can use anything really. So it's the same thing for the activation functions. As long as it's nonlinear and it's monotonic, you can use anything you want. It just happens that this is what we've settled on as a community on what works best, right? Yes. You would use the same for multi-class. I'll discuss how to do multi-class in a minute. Yeah, good question. Or at the end of the lecture, probably. I don't think it's in the slides. Yeah. Any other questions? Okay, cool. Oh, this is, all right. I didn't make these slides, so I'm going to say some things repeatedly, or I'm going to skip some things. But this is the concept behind vanishing gradients, where the deeper your model is, right, the less and less gradients you get with certain activation functions like tanh and sigmoid. And then you can't update layers earlier in the depth of the model because you lose the gradients, because the gradients get smaller and smaller and smaller over depth just by the nature of it. Okay. Oh, come on. Okay, yes. All right, this is exactly what I said already. ReLU in the positive region, ReLU doesn't saturate at all, so you always get a gradient for positive input. In the negative region, ReLU just becomes 0, but it dies. But this doesn't become a problem because the earlier units change anyways, and then they come alive again and whatnot. Yeah. All right, let's talk about normalization. Okay, so for training neural networks, it's especially important to normalize your input. So if you remember when you did SGD, right, for learning that linear model, like for homework 1 and homework 2, there's at some point where we said if you normalize your data set to have a mean 0, standard deviation 1, that's going to kind of stabilize your model a little bit. It's the exact same thing for neural networks. So especially for sigmoid, right, we want to keep the inputs where the maximum gradients are, right, so that it trains our model the most, and we avoid the vanishing gradient problem, right? So we try to normalize, we can normalize our input so that at the input stage, it always fits in that shaded region for sigmoid, right? You can actually do this at each step. So we can do this every time you apply the activation. Okay, it's going to go into batch norm. So after each activation function, so after sigmoid, if you look at the distribution of your values and you shift them every single time so that they're centered at 0 and then have a standard deviation of 1, you can kind of prevent those values from escaping out into those low gradient regions of sigmoid, right? So this is called batch normalization. So this is what I briefly mentioned before when we said you can feed in multiple data points. But if you want to do this type of normalization, you need to have some sense of what the mean should be and what the standard deviation should be, right? But you can imagine that this is intractable for large data sets, right? You can't calculate the mean of the entire data set every single time for every single application, for every single neuron in your layer, right? So what we do instead is we feed in 16 data points at a time. And then for each time they go through the activation function, we take their mean, we take their standard deviation, and then we normalize those activation values, the outputs, back into mean 0, standard deviation 1, right? So we do this at each layer for the specific input that you've fed in. So if you fed in 16, for those 16 data points will normalize to their mean and standard deviation at each layer, not just at the input. Okay, and so we refer to this as batch normalization. So the original idea for suggesting this, and this was suggested in 2015 by I can't pronounce his name, Segedi. He's really famous. I feel bad now. Anyways, very prominent researcher proposed batch normalization in 2015. So this is fairly recent in our memories, but in the history of neural networks, like Krzyzewski et al. Was 2012, right? So this is like a long time ago in terms of neural network research. The original intent of this is to do exactly that, is to keep the values inside this shaded region so that we maximize the gradient. What actually happened is that, well, okay. So again, the original motivation of this was to stabilize the activation so that they're not going all over the place, right? They're not going super high values, super low values. They kind of relatively stay inside this middle region during training, right? And then what they say here as well, the internal covariance shift, where, like I said before, if a previous layer changes significantly, now that second layer doesn't learn as well anymore, right? Because its definition of the world has changed because the thing that defined its world, which was the previous layer, changed significantly, right? So it was meant to fix this, but actually it doesn't really seem to fix this at all. In fact, if you train a model with or without batch norm, it doesn't fix internal covariance shift at all for whatever reason. But it does seem to stabilize and smooth the optimization surface. So it seems to somewhat regularize the model so that it trains better and it trains faster. This is one of those things where we don't know why, or there's no consensus on why this works exactly, but we just know from empirical evidence that this seems to help. So we tend to include it in our models. We're generally training with batch sizes anyways, right? Because that helps us with the compute. So we might as well get some free regularization while we're at it. It might be the case, these slides haven't been updated a bit, so it might be the case that we've proved this in the last couple of years, but I doubt it. I would have known about it. So I think we're still debating, but this is a topic of ongoing theoretical research on why this works and what are some different ways. And you'll see a lot of variations, like people have proposed, okay, let's do batch normalization, but let's do it this way instead, or let's use this instead, or things like that. Speaking of regularization, yes?
So I know for things like transformers, layer norm is kind of what they do. Do you know if it's for a similar reason to this, or it doesn't actually handle?
I'm not familiar with that. If you come to office hours, we can look it up together if you'd like. But yeah, I know what you're talking about. So for transformers, which is a different, anyways, we won't get into that. That's its own thing. But yeah, so I know layer norm was a thing for transformers. I don't know exactly how it's related to batch norm or if it actually solves the problem that it claims to solve. Or again, it might be one of those, hey, we tried this thing and it works really well. Yes. That's a good question. So I'd counter that by saying that's happening anyways, right? Because, so let's just look at layer 2, right? So layer 1 is learning already. So its output is already changing significantly, right? Oh, shoot. And then the batch norm is just, it's not changing those values. It's just squeezing the distribution so that it better fits that mean and standard deviation range. But the actual, I guess, like the actual values themselves are still like relative to each other. Like that signal still stays there. We're just shifting the distribution to fit kind of the expected input better, right? I could have probably explained that better. If you come to office hours, we can kind of talk about it. But kind of the point being, yeah, yeah, come to office hours. We'll talk about it a little bit more. Yeah, okay. Good question though. Okay, so let's talk about regularization, and I'll try and get through it a little bit quickly here. So we've talked about regularization before for linear models, where we combat overfitting by preventing the model from overfitting to the noise. But neural networks are ridiculously flexible, like very, very, very flexible. They will fit anything, okay? So there's a lot of research into neural network regularization to help them generalize better and to prevent them from fitting the noise. So batch norm was one such thing, although the intent wasn't to regularize, the effect is that they do regularize. Turns out stochastic gradient descent is actually a regularizer for neural networks. We don't really know why. There was a paper in 2021 at NeurIPS that tried to explain it. But for some reason that I'm not going to get into now, I haven't read that paper either. But doing stochastic gradient descent compared to just doing gradient descent on neural networks seems to provide a regularizing quality to the neural network. It seems to learn a lot faster. It seems to be a lot more generalizable, et cetera. Something about descending into the loss surface helps it escape local minima and find the better global minima. I'm guessing that it can probably escape kind of local minima better, right? So it does a better job of searching around for a global minima instead of just getting trapped into the first local minima that it sees. You can also imagine some adversarial cases. So for example, this is an online algorithm, right? So if the first 50 points in your data set are all negative examples, and then the next 50 are all positive examples, what happens, right? That's on your homework. Answer that on your homework. Okay. And then we also have something called dropout, which is also extremely interesting. And dropout was responsible for some significant performance gains on specific tasks, kind of early on, and especially CNN research. Dropout is where we just turn off neurons randomly during training. And we're not talking like 5%. We're talking like 40%, 50%, just neurons. Nope, you don't get to update your weights right now. These other neurons are going to do the learning. And so the intuition there is that you don't allow the model to just use like 2 or 3 nodes to do all of the learning, and then everything else, you're kind of forcing the neural network to distribute its learning amongst the different nodes, right? Because it's not like it can't use all the nodes to learn, to do the training pass every single time. But again, it's one of those things where there's a lot of research, a lot of different people have tried to explain it mathematically, but in general, we just know it works really well. So that's why we use it. Although I think it's fallen out of favor recently. I think some other tricks have replaced dropout in terms of learning models. But initially, it was very, very popular, like 50% dropout. You would see on I think Krzyzewski, like the original ImageNet model had like 40% dropout in the middle of its training, something like that. Okay. We can also provide constraints. So we can do early stopping, which, as you might know, same thing as when you implemented SGD, where you don't train anymore once you see that the validation loss isn't going up, but the training loss is improving. because that just means you're overfitting to the training set. You're not doing any better on the validation set. So that's one easy way of doing it. A lot of deep learning frameworks will have a function for doing this automatically. You just set what epsilon it is, and it says, okay, if the validation loss doesn't improve by this epsilon within 3 epochs, I'll just stop. There's a lot of solutions like that. And then there's also weight penalties. So we can do L2 regularizations on the weight itself. I'll just leave it at that, and then we can talk about that a little bit more. Okay, weight initialization. I'm going to go through this one really quickly. Since we're learning with this kind of gradient descent way, it does matter where you start your weight initialization. If you start them all at 0, there's no gradient, right? Because everything multiplies out to 0, so that's bad. So we want it to be something not 0. If you look in the literature, there's a lot of different functions with people's names attached to them where they say, oh, if your data set is this large and your batch size is this, then your weight should be that. In general, if you just uniformly distribute or Gaussian distribute, it'll learn eventually. But there's some strategies for making that go better or worse. You can look that up. Okay, for optimization, so far we've talked about SGD, right? And that's what we used so far, where we just calculate the derivative and we update the weights correctly. There's some variants now that use something called memory, where it remembers the previous gradient update and it includes that in considering the new gradient update. So the better term for this, in my terms, is momentum. This is what Atom is, or like RMS prop, I think, does this also. Where if you imagine literally from a physics standpoint, and this is supposed to be an animation, but I'm on like a Ubuntu laptop, and the slides are made in Keynote, so none of the animations play. But if you imagine this as like a physical model, like literally a marble, falling down a slope, right? In physics, right, we're not just looking at the gradient at each step and like updating it, right? There's momentum, like there's a velocity that the marble is going at already, and then the new gradient of your surface contributes to that momentum, right? Same exact way. They've developed optimization schemes that include some momentum term so that a single batch can't like completely change the direction of your optimization, right? It still follows a general momentum downwards. And this stabilizes your optimization a little bit. It doesn't get so noisy and unstable. Okay. I think Atom is like a pretty plug and play one. You don't even have to set the learning rate because it learns the learning rate by itself. So that's like a pretty cool thing that you can use. It's like a pretty easy replacement for SGD, but it's not like it's guaranteed to find the better solution, right? It might find the solution a little bit quicker, right? But it's not like a complete replacement for SGD. Like I still train some models with SGD because Atom doesn't seem to be showing any kind of significant improvement. Okay, all right. So this is kind of getting into neural network architectures, and we have 10 minutes remaining, so I'll kind of get through these quick. Sequential connectivity, so everything we've talked about so far, we call a fully connected layer or a fully connected network because everything, it's perfectly sequential, right? Each layer takes in the output of the previous layer, et cetera, et cetera. Recent work has developed these different links that you can provide between layers. So you don't have to go A to B, B to C, C to D. You can actually create skip connections where you add in a highway or a skip connection for a layer output to skip like 5 layers forward and like be concatenated with previous layers output and go forward. Now, why would you want to do that? If you're training like a ridiculously deep model, like we said before, as the model gets deeper, the gradients kind of get worse and worse and worse, right? And they get kind of saturated and such. So if you provide these skip connections, it provides some path for some information to travel and skip so that you get a more stable training and you get a more stable gradient. With ResNet, that's the HAL 2016, that's kind of what it looks like, right? It literally skips over some layers and then gets concatenated. And then the densely connected convolutional networks is not as popular because it's very computationally expensive, but you basically have a dense number of skip connections going from layer to layer. Okay, so we're moving on from tips and tricks to a buffet of ideas. Oh, okay. So these are some kind of advanced topics that you might want to look into because there's been a lot of research activity in them lately. Um, so attention, you'll see this a lot in natural language processing, where in soft attention, you add some weights, right? You basically add some kind of a mask, almost like a weighted mask, where you specify the network itself learns what parts of the sentence or the image it should be looking at more, right? So think of it as like a dynamic mask that it's learning internally to the network itself. So that's pretty cool because sometimes it leads to networks where it'll say, I think this is an apple, and here's a region of the image that led me to believe this is an apple, right? Or in a lot of NLP cases, you'll have a sentence and it'll say, I thought this was a, I don't know, unhappy review because it had the words not tasty, right? Or something like that. Like the network provides some kind of explanation due to its attention mechanisms that's inside. So yeah, there's soft attention, which is kind of a weighing scheme. Hard attention, it physically cuts off the things that it should pay attention to. I'm not actually familiar with this glimpse network example here, but that's kind of the sense is it hard masks portions of the image that it should look at, and then it makes its decisions based on those hard masks, right? So attention is really important. There's a paper called Attention is All You Need, again, with these machine learning catchy titles, if you kind of want to know what attention is capable of, and there's a lot of literature on that as well. But that one famous paper is called Attention is All You Need. And then there's a paper called Attention is Not All You Need. And then, you know, that's how these machine learning conferences go. Okay. All right. So far we've been talking about in this course differentiable loss functions. And that's because for gradient descent, your loss function needs to be differentiable. But there's a lot of tasks where that loss function is not differentiable. So for example, we have stochastic operations, we have discontinuous operations, right? So if you have that, if you need to learn a function where it goes from 0 to 1 and you can't do a logistic for some reason, so you have that straight line that has infinite gradient, or non-analytical operations, that is like the entirety of reinforcement learning. So where you're trying to get an AI to do Atari, for example. What is it going to do here? Okay, yeah, so this is, again, a huge field of research, especially for reinforcement learning, because reinforcement learning is huge for robot control learning, for learning robot control, right? And then as well as for game playing, so you know, playing Atari games and things like that, or any self-driving cars is like reinforcement learning, you could argue, right, etc. So this is a huge field of research as well if you're interested. Some ways that they've gotten around this, I don't see how this is useful at this point in the lecture, but anyways, basically you can define this space as an integral, and then you can like differentiate that integral. But it involves estimating that kind of non-differentiable loss function as an integral, and then taking the derivative of that. So I won't go into all the math here because I don't think it's very useful at this point, but the slides are online, and if you want, you can look up the papers, or at least you know the keywords to look up if you're kind of interested in non-differentiable loss functions. And then I should also note that your loss function doesn't have to be a function at all. It can be a whole nother network, and that kind of leads into generative adversarial networks, or GANs, right, where your loss function is a network that's also learning as your generative model is learning, right? So it can get really interesting and complicated. And then we have a section also on learning to optimize. So we've talked about SGD and Atom as optimizers for doing kind of traditional gradient descent with or without momentum. Turns out you can actually use a model to do that learning itself. It's kind of framed as meta learning, if you will, where instead of just doing SGD, you do a model. Again, I'm sure there are tasks for which this is appropriate, but this is pretty heavily into the bleeding edge research field where we're kind of looking at it theoretically, or there's some niche task where this is really required. But mostly SGD will get you there 95% of the time. Ooh, this is something I was personally interested in. It's called adversarial examples. So because neural networks are so high capacity, right? at the end, the surface that it's learned, you can kind of imagine it learns some hyperplane for some decision making, right? Some n-dimensional nonlinear hyperplane. But this hyperplane is not smooth. Like it's very noisy, it's very complicated, right? There's a lot of, if you imagine the hyperplane in three-dimensional space, you can imagine it as very rough and spiky, right, almost. So it's possible to train a model to take advantage of that non-smoothness of that decision surface. So the example that's shown here, on the left you have a picture of a panda, and then if you add that seemingly random noise with some epsilon so that it's imperceptible, on top of that panda image, a neural network will predict it as a gibbon, right? And that's because a model has learned that noise image to optimize that overall image to be misclassified, right? So this is like really interesting. So you're taking advantage of the over-parameterization of the neural network models. It's like so high capacity that it has pockets where it makes errors. The example on the right is some research, I think it's out of Stanford, don't quote me on that, where you add some stickers to a stop sign and a self-driving car model will like misinterpret it as a speed limit sign instead or something like that. Even though you would think a stop sign is like a really obvious thing, because it's a neural network, it has all these pockets that can be taken advantage of, right? This is a whole field, adversarial neural network robustness. It's very interesting. It gets very theoretic. I spent like a year like dabbling in it, and it's pretty fun, I think. And there's also like questions as to, do you have access to the model when you do it, right? Do you have access to the losses and the gradients, et cetera? That's interesting. Bayesian neural networks. So if you're familiar with kind of Bayesian models, this is that combined with the neural network, so you can maintain some uncertainty quantification throughout your model. So not only does it predict the value, it predicts how uncertain it is about that value. Oh, an interesting note on generalization. So remember how I said a neural network is very high capacity, right? It can be super over-parameterized. This graph here shows the loss with respect to training time. So this is the number of epochs, and that's the training loss on the y-axis. This blue here is the original data set with the actual labels. But the purple here is with random pixels, just random pixels with the same labels. And then on the red here is the same images, but with completely random labels, right? So conceptually, the purple and the red, there's nothing to be learned, right? On the purple, it's random data, and on the red, it's random labels. And yet, given enough training steps, the model will completely learn the problem. It will completely memorize the training set, even though to our brains, there's no semantic correlation between the input and the output, right? So one thing you have to be careful with when developing neural network models is, even if you messed up during your data ingest step, like when you were reading your training data and your training labels, even if you messed up, if you train your model, it'll like learn it perfectly. And then you'll get like a very reasonable convergence graph. And then you'll try it on the validation step and like it won't work at all, right? So just be careful. It's very good at overfitting, essentially, to random noise. Okay, this is the last slide, and I'll let you go. So the concept of information bottleneck is that deep networks, in the process of learning to do their tasks, also learn representations that compress the input. It does some kind of dimensionality reduction, okay? So for example, if I take a neural network that's like multiple layers, so you have some input image, and then you have layers, and then it does some classification at the end. If you actually take the weight activations at this last layer, that serves as a really good vector representation of the contents of this image, right? And so that's how image embeddings work. That's how Google's like search with this image works, like where you can upload an image and it'll find similar images. It's using a neural network to embed that image into a vector of numbers, and then you can calculate the similarity between vectors with like cosine similarity, and you can search for similar images. So that's kind of an idea of the information bottleneck theory, where by the process of learning, the neural network also learns to reduce the input into a smaller dimensionality space. Okay, cool. The rest is history stuff. You can look up on the slides. I think I will say it is very neural network centric history of machine learning, right? Like it's kind of like, and then SVM happens, but then deep learning saved the day, right? So take that into account, that it's a little bit deep learning centric. I think random forests and SVMs late 90s, early 2000s should also get a lot of credit because for the majority of problems, they're enough. But as you all already know, deep learning has made a lot of strides. Here's a summary slide of everything we've talked about. Deep learning is cool, but there's a lot left to do. I know ChatGPT has been, all right, this is kind of high level stuff, but I know ChatGPT is in the news, but again, to me, it's not very impressive because it's just continuation of, I mean, it is impressive, don't get me wrong, but like it makes sense, right? It's a continuation of existing work. It makes sense that that's where we are now, but we have got a long way to go if it's going to actually start saying sentences that are true instead of just like realistic, right? Okay. Next time, CNNs and RNNs, which are different architectures for different tasks. Yeah, thanks for coming. Sorry for the extra 3 minutes.